Hi, Assalamualaikum and welcome back to my channel Physics from 5 KSSM. Today we continue 3.2 Resistance Part 3. In this video I will discuss one learning standard. Describe factors that affect resistance of wire through experiment to conclude R equals rho L divided by E. So in this video I will discuss three experiments, experiment 3.2, 3.3 and 3.4. Okay, let's look at factors affecting resistance. The first factor is material of conductor. How this factor, material, affect resistance? For example, silver has the least resistance but very expensive to use in wires. So most conducting wires are made from copper. So different type of material will have different resistance. Second factor is temperature. As temperature of wire increases, its resistance increases and its conductivity decreases. As we know, resistance opposes the flow of current. As resistance increases, the current decreases, thus conductivity decreases. In other words, a colder wire is less resistant than a warmer wire. The third factor is length. The difference between the shorter and the longer wire. The longer wires offer more resistance than shorter wires. If the wire doubles in length, it doubles in resistance. We will discuss later the relationship between resistance and length of wire. This one is cross-sectional area, meaning the thickness of wire. The cross-sectional wire can be represented by standard wire gauge. The numbers labeled for standard wire gauge represent the thickness of wire. Wider wires offer less resistance than thinner wires. If the wire doubles in width, its resistance is half as great. Conducting wires that carry large currents need large diameters to lessen their resistance, meaning the thinner the wire, the higher the resistance. Okay, let's look at further about the factors that affect resistance. The first factor that we want to discuss is length of conductor. Let's assume we have same type of material of wire and same thickness of wire, but now we have different length of wire, L, 2L and 3L. If compare the resistance of the wires, we get for L is R, so when the length is double, resistance also double. When the length is triple, resistance also triple. Thus, we get this relationship. Resistance is directly proportional to L, or length of wire. Temperature. How temperature affects resistance of conductor? The higher the temperature of conductor, the higher the resistance. Resistance increases with temperature of the conductor. We have this graph to show relationship R against temperature. So you can see increases with temperature. As we discussed earlier, warmer wire has higher resistance compared to colder wire. The cross-sectional area. The bigger the cross-sectional area A of a conductor, the smaller the resistance. Resistance is inversely proportional with cross-sectional area of conductor. As you can see, we have same type of material wire, same length, but different in thickness of cross-sectional area. If the thickness is double, resistance is half, and so on. When you look at this one, the graph, R inversely proportional to cross-sectional area. If we plot a graph of R against 1 over A, so we get R directly proportional to reciprocal of A, meaning 1 over A. For this graph V against I, as we know that for this graph, the gradient of the graph is equals to resistance. If we have three different thickness of wire that represent by SWG. What is this SWG? Standard wire gauge. The diameter of wire is shown by SWG unit. When the value of SWG increases, the diameter of wire decreases. You can look at example in this table. SWG 24, diameter is 0.599. SWG 26, 0.457. SWG 30, 0.315 millimeter. So all have its diameter fixed for the certain value of SWG. So SWG increases, diameter decreases. Okay. So fine wire, medium wire, and thick wire. So look at the gradient of the graph. For fine wire, gradient is the highest, meaning resistance is the highest. So SWG 32 has highest resistance compared to SWG 29 compared to SWG 22. So from here we can say R is inversely proportional to area or cross-sectional area. Okay, material of conductor. Resistance of conductor changes with material of conductor. Let's say we have different type of material, same length, same thickness, constantan wire and eureka wire. So same length, same thickness, but different in resistance. So you can see from here, resistance of eureka wire is the highest compared to constantan, compared to copper. So it depends on type of material. If you have this graph V against I, for V against I, the gradient of the graph equals to resistance. So the graph that shows a larger gradient means a larger resistance. So from here we can compare resistance of nichrome, constantan, copper and silver. So from here, gradient the highest is nichrome. Thus nichrome wire has higher resistance. Silver has the lowest gradient, thus lowest resistance. Okay, so meaning the type of material or material conductor also one of the factors that affect resistance of the conductor. Okay, let's look at experiment. The first experiment is experiment 3.2. You can refer to your textbook. Let's say we have these two diagrams. So between these two diagrams, what can you say about the brightness of the bulb? The situation given, a garden lamp lights up brightly when it is connected to solar panel. Diagram 4.2 shows identical lamp lights up dimly when connected to the same solar panel. Okay, so you can see the length of the wire are not the same. The second diagram has the longest wire compared to the first diagram. Okay, let's look at inference. Inference is based on this situation given, diagram 4.1 and diagram 4.2. What we can say about the situation given? So from here, we can say resistance of the wire is depends on length of wire. Hypothesis, the longer the wire, the higher the resistance. Or you can write as, when the length of the wire increases, resistance of the wire increases. Okay, that one is hypothesis. Aim of this experiment to study relationship between length of wire and resistance. Manipulated variable length of wire, the symbol is L. Responding variable resistance, symbol is R. Constant variable means other factors that affect resistance must be kept constant. Diameter or cross-sectional area of wire. Resistivity represent material of wire and temperature of wire. Apparatus and material, we need two dry cell, 1.5 volt, dry cell holder, switch, connecting wire, ammeter, voltmeter, crocodile clip, rheostat, meter rule, constantan wire of SWG24. Look at the arrangement. Constantan wire about 1 meter is attached to a meter rule and placed at the end of both ends. Okay, so what we do, we just connect the circuit to the battery of 3 volt, for example. This is a switch, ammeter, crocodile clip, rheostat to control current. One end of the crocodile clip is connected to the end of the wire at the 0 mark of the meter rule. Okay, and then the second crocodile clip, you can move it to change the length of wire, because in this activity we want to relate between length of wire and resistance. And then across the wire we connect to voltmeter so that we can get reading of voltmeter. The procedure: arrange the apparatus so that length of wire L is 20 cm. Close the switch and adjust rheostat until current flowing in the circuit equals 0.2 ampere. Record value of voltmeter. Calculate resistance R equals V divided by I. Repeat experiment L 40, 60, 80 and 100. Okay, let's watch the video to show how this activity can be carried out. Okay, these are the apparatus required for the experiment. We have the connecting wire. Now we want to complete the series part first. Connect the battery or dry cell to ammeter. And then you connect to one end of the wire at the meter rule. The wire is already attached to the meter rule. Okay, we have completed this part, and then we want to complete the whole circuit for the series part. The use of different wire is to differentiate between positive terminal and negative terminal. Okay, so the crocodile clip is attached or connected to both ends of the wire at the meter rule, because the first value that we want to use is 100 centimeter. So it depends on what value that we want to use. So for this experiment, the first value of length is 100 centimeter. Okay, now already completed for the series part. Okay, next connect a voltmeter across the wire. Okay, so we have completed the circuit. Okay, the first value for length is 100 centimeter. For first value of 100 centimeter, you can record the reading of ammeter and reading of voltage. Current is 0.08. For the voltage is 4.71 volt. So how to change the length? So you move one end of the crocodile clip and clamp it to the 10 cm reading, so that the total length become 90 centimeter. So now it's 90 centimeter. Okay, record the reading. Current 0.08 ampere. Now the voltage is 4.63. Now change to ATM, so we get the reading of the voltmeter is 4.51. Okay, for 90 cm we get the reading of the voltmeter is 4.63, current 0.08. For 80 cm we get voltage 4.51 volt, current 0.09. For 70 cm, we get 4.4 volt and current 0.10. For 50 cm, voltage 4.09, current 0.14. For voltage 3.88, we get current 0.16. And then for 30 cm, we get voltage. We just move the crocodile clip to clamp to the required length. You can record the reading of voltmeter and ammeter. So if you have rheostat, you can adjust rheostat to constant the current. If not, you just can record reading of the ammeter and voltmeter at the same time. So you also can get the readings. Okay. From there, you can calculate resistance of wire. by using the formula voltage divided by current. So R equals to V divided by I. So from the result that you get, you can plot a graph of R against L, resistance against length. Okay, state a precaution that needs to be taken to ensure that wire temperature is constant throughout experiment. What we do, open the switch of the circuit if not taking any reading, so that temperature of the wire does not increase, because we don't want the factor temperature to affect the reading of voltmeter, okay, during this experiment. So it cannot get accurate result. Temperature must be kept constant. Okay, so other than that, we can have something like read the scale of ammeter and voltmeter with eye level perpendicular to the scale of ammeter or voltmeter to prevent parallax error. The temperature must remain the same throughout the experiment, because an increase in temperature will increase resistance of the wire. We just want to discuss one factor in this experiment, that is length. So we must keep other factors constant. Temperature, diameter, okay, and material of wire must be kept constant. Okay, let's say we have this set of answer. You can look at the value that we get from the experiment. The length that we use is 20, 40, 60, 80, and 100. Use rheostat to adjust current to constant value 0.5 ampere. So for each length of wire, record reading of voltmeter. Okay, the reading depends on the accuracy of the voltmeter, sometimes 2 dp, sometimes 1 dp. Okay. And then from the value that we get, calculate resistance of wire. R equals V divided by R. So this is the reading of resistance for this experiment. So based on the table here, plot a graph of R against L. So this is level R against L. Okay, mark the scale correctly. Transfer all points correctly. Draw best straight line. So we get a straight line passes through the origin. What conclusion can be drawn from this experiment? The length of wire is directly proportional to resistance of wire. Okay, the second experiment is experiment 3.3. Look at this picture. Diagram 4.1, 4.2. Incubator connected to 240 volt power supply by using thin copper wire. Diagram 4.2 shows same incubator connected to 240 volt power supply using thick copper wire. The light bulb lights up brighter. So the same length of wire used here, but different thickness. So the factor that affect resistance in this diagram is thickness or cross-sectional area of wire. You look at the brightness of the bulb. Okay, this one become brighter when using thicker wire. Become brighter because of resistance is smaller. Okay. Inference: the cross-sectional area of wire influences resistance of wire. We must put area here, the cross-sectional area of wire. Hypothesis: the larger the cross-sectional area of the wire, the lower the resistance. Aim of this experiment to study relationship between cross-sectional area with resistance of wire. Manipulated variable cross-sectional area of wire A, responding variable resistance R, constant variable length of wire, resistivity of wire, temperature of wire. So all these factors must be kept constant. Apparatus: actually apparatus required quite the same, only we just add a different diameter of wire that represent by SWG. Okay, so constant wire of SWG 22, SWG 24, 26, 28, and 30. Setup of apparatus are same with the first experiment 3.2. So the difference is the wire, the constant wire here, you just change to different thickness of wire. For the first experiment, we change the length. So for this experiment, we just change the thickness of wire of cross-sectional area. The setup are the same. Okay. Procedure. Connect 25 cm length of SWG22 between P and Q. So this is the constant wire. Close the switch, adjust rheostat until current I flowing in the circuit 0.5 ampere. This is rheostat. Record value of potential difference across the wire, the value of V. Calculate cross-sectional area of wire. A equals to pi r squared. R is the radius. Given normally is diameter, so you need to calculate the radius first, then only you calculate the area. Resistance R equals V divided by I. Repeat experiment using SWG 24, 26, 28 and 30 of constant wires. Okay, this is a table. For SWG 22, 24, 26, 28 and 30, it has its own diameter. It's already fixed diameter for certain SWG. Okay, so you can look at the value, meaning the larger the number of the SWG, the thinner the wire. The cross-sectional area you can calculate using pi r squared. This is D is diameter, so you need to calculate for radius, then you apply formula pi r squared. So you get this value. Okay, all values, calculated value, you must state in 3 significant figures, 2 to 4 decimal places. Okay, 1 over A, 1 over cross-sectional area. So you just calculate using calculator, 1 divided by 0.397, so you get 252. So this one also minimum is 3 significant figures, 2 decimal places. Okay, current I, the value is already fixed. You can fix it to 0.5 ampere. You can fix it to 0.1 ampere. Okay, depends on what value you use. And then record a potential difference for every SWG, for every cross-sectional area of wire. Look at this one. And then calculate resistance. Resistance equals to V divided by I. So 0.04 divided by 0.1. And then you continue to complete the table, so you get this value of resistance. Okay, based on the table, you can plot 2 graphs. You can plot resistance against cross-sectional area. You also can plot a graph of resistance against 1 over A. Okay, let's look at the graph. For the first graph is R against cross-sectional area A. R against A. Okay, you can choose a correct scale for you all to plot the graph. The graph must be large enough. Transfer the points correctly and then draw the straight line. Okay, from the distribution of points, we also can see the graph is a curved graph. So we get this graph. For the second graph, R against 1 over A. Transfer all the points. Okay, draw a best fitted line. So we get this graph directly proportional to origin. Okay. Based on the graph that we get, what can you say about the relationship between R and A? Okay, discuss some of the question first. What is presented by the value of SWG, standard wire gauge? SWG represent diameter for each wire. State the relationship between value of SWG and diameter. The larger the value of SWG, the thinner the wire. Based on the graph, we can say R is inversely proportional to cross-sectional area. This is the graph that we get. R against A, we get R inversely proportional to A. From this graph, R against 1 over A, we get a straight line passes through the origin, meaning R is directly proportional to 1 over A. Okay, the third experiment in this topic is experiment 3.4. We want to discuss on the factor material of wire. The material of wire represented by resistivity of wire. So the inference we can write here is resistance of wire depends on resistivity of wire. The greater the resistivity of a conductor, the greater the resistance. Aim to study relationship between resistivity and resistance. So manipulated variable, we use different type of wire, meaning resistivity of wire, rho. Responding variable, resistance, R. Constant variable, length of wire, cross-sectional area of wire, and also temperature. Apparatus required, okay, same as the experiment before, only we change to different type of material, constantan wire, nichrome wire, or you can add some more like copper wire. So you have different type of wire. Okay, procedure, arrangement still the same. Setup apparatus as shown in diagram. Adjust length of constantan wire so that length L is 30 cm. We want to fix the length. Close the switch, adjust rheostat until current flowing 0.5 ampere. Record the voltmeter reading. Calculate resistance R equals V divided by I. Repeat experiment with nichrome wire. If you want to have a 5 set of data, so you can have 5 different type of wires. In this experiment, we just use 2 types, constantan and nichrome, just to differentiate between different type of material. So constant current 0.1. Record the value of V for every type of wire. So we get for constantan 0.06. Thus resistance V divided by I equals to 0.6. For nichrome wire, 0.16 divided 0.1, so we get 1.6. So what conclusion can be drawn from this experiment? Okay, we just compare the value from the table here. No need to plot a graph. Okay, so what we can say, the resistance of nichrome wire is larger than constantan wire. So based on the result of experiment 3.2, 3.3, and 3.4, we want to relate between R and L, R and A, and also R and rho. Okay, the first experiment 3.2, R is directly proportional to length. From the second experiment, R is directly proportional to 1 over A. Combining these two results, so we get R directly proportional to L divided by A. This is relationship. Okay, for the experiment, if you use same type of material, thus the constant here is resistivity of wire, or the rho is a constant value. Thus we can write as R equals rho L divided by A. So rho is resistivity of the conductor. If the experiment for experiment 3.2 and 3.3, if we use the same type of material, for example constantan wire, so the rho here is resistivity of constantan wire. So we have proved the formula that relates between R, rho, L, and A. So from here we can see clearly the relationship. The first, the relationship between resistivity or type of material, length of wire L, and cross-sectional area. So this formula already summarizes the whole points that we discussed today about factors affecting resistance. Okay, so that's all my video today on factors affecting resistance about experiment. I will continue next part 4 in my next video. Thank you for watching. Bye.